Let's take a look at some reactions. Here we have a solution of silver nitrate, and here we have a solution of silver chloride. Silver nitrate is soluble in water. If we look at our solubility rules, it states that all nitrates are soluble. So silver nitrate exists in solution as free silver ions and free nitrate ions. Sodium chloride is also soluble. If we look at our solubility rules for chloride, it says that all chlorides are soluble except silver, lead, and mercury. Sodium is not one of those exceptions, so sodium chloride is soluble. So it exists in solution as free sodium and free chloride ions. If we were to mix those together, then all of those ions are free to intermingle. And when we do that, we see this fluffy white solid crash out of solution. That fluffy white solid is silver chloride, because the pairing of silver and chloride results in something that's not soluble. If we look at our solubility rules, it says that all chlorides are soluble except silver, lead, and mercury. So that means that when my silver pairs with my chloride, that results in something that's not soluble. And we see that crashing out of solution as a fluffy white solid. That is a precipitate. The sodium and the nitrate, we pair together those ions, and that does not result in a solid. Okay? All nitrates are soluble, and there are no exceptions there. Okay? If we were to write a balanced chemical equation to represent what we did, we would probably write something that looks like this. A solution of silver nitrate is mixed with a solution of sodium chloride to produce solid silver chloride and a solution of sodium nitrate. But if we wanted to communicate about what's happening sort of at the atomic or molecular level, we could write a total ionic equation, which is going to represent everything as it appears in solution. Okay? So everything that has an AQ label is going to be separated into its component ions to reflect how it exists in solution. So silver nitrate has an AQ label. It separates into silver ions and nitrate ions, as we see up here. Okay? Silver ions in solution, nitrate ions in solution. My sodium chloride exists in solution as free sodium ions and free chloride ions. Okay? So we've got sodium ions in solution and chloride ions in solution. If we look closer, one molecule of silver nitrate breaks apart into 1 part silver and 1 part nitrate. So we have 1 silver here and 1 nitrate here. Sodium chloride is made up of 1 part sodium and 1 part chloride. So we have 1 sodium and 1 chloride. On the other side here, we're looking at this beaker here, our silver chloride we're going to leave alone. We're going to leave it together as a solid, okay? Because that's how it's existing. We have our silver chloride that's paired together as a solid. Our sodium nitrate exists as free sodium ions and free nitrate ions. Again, 1 part sodium, 1 part nitrate. 1 sodium, 1 nitrate. Notice that at no point are my state labels changing here. Okay. My silver is existing in solution as an ion, not as a solid. Okay, so make sure that when you're working with ionic equations that you have charges where necessary. Okay. If we wanted to focus in on just the things that are involved in making this fluffy white solid, let's ignore the things that don't change over the course of the reaction, the things that remain unchanged on either side of that arrow. Okay. Well, I've got nitrate on both sides here that look identical. So I'm just kind of marking through them just to kind of keep track of what I'm ignoring here. My sodium ions also appear unchanged on either side of that arrow. Okay. If I were to ignore what I've just kind of marked out and didn't write those in there, I would have what's referred to as my net ionic equation. My net ionic equation is representing what comes together to form the observed precipitate. Okay. There are also cases where ions come together to form a liquid or a gas, but the majority of the problems that we're going to be doing result in the formation of a solid. Okay. So your net ionic equation is showing you what's actually coming together to form the observed precipitate. Okay. We can see that my silver ions came together with my chloride ions to form my precipitate. Okay. And this is still balanced, as is the ionic equation. At every point in this, you want to double check to make sure that you haven't violated the law of conservation of mass, that you have the same number of atoms on either side of that arrow. Make sure that your charges balance as well. On the left side of my arrow, 1 positive plus 1 negative gives me something, sums to 0, which matches my neutral charge on my other side. Okay. These things that I marked out and ignored, those are called spectator ions. They're there, okay? But they're not participating in the reaction. It's like a football game. The game can go on without the spectators, without the fans, but it can't go on without the players. So your spectator ions are ions that are there but are not participating in the solution. And so we ignore those when we write our net ionic equation. But they do appear in our total ionic equation. Our total ionic equation is representing all of the ions that are present, not just the ones that are playing. That's the role of the net ionic equation.